So how whatever I was doing there, right? So I was dividing the sample space in different partitions. So what I was showing you here is that I've got 1, 2, 3, 4, 5, 6. So this was my sample space, and I have divided my sample space into various smaller events or partitions, wherein I'm calling this E1 is 1, E2 is 2, and E3 is 3, and E4 is 4, and E5 is 5, and E6 is 6. Then there is another thing which is there for this events which I'm showing you, the partitions. They are actually mutually exclusive, so there is nothing common between them. E1 intersection E2 is 5, E2 intersection E3 is 5, and so on and so forth. I mean, in general, what I say here is that EI intersection EJ is 5. So if I take any I or J where I is not equal to j. So this will be giving me a 5. So they are mutually exclusive. And in general, whenever there are simple events, right, they are mutually exclusive. So of course, there is nothing common between 1 and 2, 2 and 3, and so on and so forth. And then there is another thing which is going on here is that E1 union E2 union E3 union E4 union E5 union E6, okay, is actually equal to the sample space itself. Okay. So combining both of these together, we can say that EI and EJ, basically EI, EJ, basically all these partitions what we have created are mutually exclusive and exhaustive. So what this gives is the exhaustive events, right? What this gives is the mutually exclusive, right? So this is how my partitioning is. So I create a partition in such a way that there is none overlapping partition here. And in this case, if I'm interested in knowing something about an event, which is A, like this, so I want to know the probability of this event. Okay. So what we are saying that we are interested in knowing the probability of this event. And what we can do with this event is that, can I say this that A is actually, this A is actually equal to S intersection A. Can I say that? Can I say that A is actually equal to S intersection A? Oh, it's as is the set which is having say 1, 2, 3, 4, 5, 6. Okay, the event, and A is the event which is having 2, 4, 6, for example. Then if I'm doing S intersection A, what I'm going to get is the smaller set. I mean, this is a subset of this, right? So what I'm going to get is that A itself. Okay, so I think here we are fine, right? S intersection A. Now what I'm doing is that I'm replacing S with all the partitions here instead of having this alone. So I'm saying that this is E1 in union E2, union E3, union E4, union E5, union E6 is what I'm writing for the timing intersection A. So what I've done is that just is replace S with this one. Can I do that? Okay. In the next step, what I'm saying here is that uh, I'm going to use what we call as the distributive law. So I'm going to write E1 intersection A union E2 intersection A union E3 intersection A union E4 intersection A union E5 intersection A union E6 intersection A. Okay. As we know that EI, E1 and E2 are mutually exclusive, then E1 intersection A will also be mutually exclusive. So all these are also going to be mutually exclusive. These are also going to be mutually exclusive. So what we are saying is that as E1, E2, E3, E4, E5, E6 are mutually exclusive, so any intersection of there with any set would also be mutually exclusive. So we can say that E1 intersection A, E2 intersection A are as well mutually exclusive. All of them are mutually exclusive. So why are we working with this? Why are we trying to say that? Because we know that if you have got PA union B, we know that for such one and if they're mutually exclusive, then we can say that it is actually equal to PA plus PB, right? So now what we are writing here is that from here what we are writing is that PA is gonna be union of all these events and they are all mutually exclusive. So can I say that this is actually equal to P of E1 intersection A plus P of E2 intersection A plus P of E3 intersection A and so on and so forth plus P of E for intersection A. Okay. Okay. Now, once we have reached here, now what I'm going to do is I'm going to you make use of what we call as the um, mul- basically multiplication theorem of probability. So let's focus on this. So if I'm saying that P E A given even if I'm wanting to write, what can I write this as? I could if two mutually exclusive events are there and B are mutually exclusive, then what happens that this P intersection B part is actually zero, right? So we remove that, right? Any mutually exclusive events, A, B, C, D, and all, right? Even if there are multiple such events, P, A, union B, union C, if they're all mutually exclusive, then I can say that the probability of this is going to be equal to PA plus PB plus PC. Okay. What we are saying is that if you're looking at some mutually exclusive events, right? So probability of all of them together, right? Or this or this or this, right? Or A, B, C is actually going to be equal to P of A union B union C is going to be equal to PA plus PB plus PC. Even if there are D, the union D would be equal to PA plus PB plus PC plus PD. Okay. Yeah. So what we are saying that these are all mutually exclusive, right? So these all sets are mutually exclusive, and then we are doing a union, right? So call this as A, B, C, A1, B1, E1, A1, B1, C1, D1, even F, right? So we are saying that as these are all mutually exclusive, so probability of A, we are trying to calculate probability of A. So probability of A should be calculated as this, right? So let me just do it in two steps if this is not confusing. So I'll say that okay. So this can be written as probability of I'm replacing A with all this one. E1 intersection A, union, E2 intersection A, union, E3 intersection A, and so on and so forth. Union, A6 intersection A. Okay, so I've just got A, so I've just replaced A with like this. Okay, from here to here. Now again using the same principle here that as they are mutually exclusive and it's a union, so probability of a union of all these events would be actually equal to sum of their individual probability, uh, sum of their individual probability. So this will be P1 E1 intersection A, P2 intersection A plus PE3 intersection A plus PE6 intersection A. Okay, we are going to use the multiplication theorem of probability. Now what we are saying that, okay, P of A given E1 would be equal to what? It will be equal to P of A intersection E1 upon P of E1. P of A intersection E1, can I say that it is going to be equal to PA given E1 into P of E1? Now I'm going to replace all of that there one by one. So we are saying that P of A is going to be equal to P of A given E1 into P of E1 plus P of E2 given A given E2 into P of E2 plus P of A given E3 into E3 and P of E3 and so on and so forth. Then it will go on until P of A given from here. For every intersection, we are writing this like this. For every uh, okay. So in general, this is what is the total probability. If you look at this, it is represented as P of A given EI into PEI, wherein your EI is varying from 1 to n. Here I've just made it from 1 to 6, but it could vary from 1 to n. So what we are trying to actually do here, we are trying to find the probability of certain event, given that I don't know the probability of it directly, but I know that some conditional probability I'm aware of. I'm aware of the conditional probability. I'm also aware of the individual probability of something. So I'm trying to make use of it. It's a reverse process of it. Okay. Had I known this, I won't use it. But somehow people are giving me the probability of these events, and they're also giving me the conditional probability of this event given this event has happened. So in such a case, we are trying to make use of it. So what are such cases as in like what are the cases in which they would it would be applicable? So there will be cases like this that there will be, for example, say there is a but maybe two bags. So there is a bag one, and it is containing four red and three white balls. This is bag one, and then there is a bag two which is containing maybe five red and two white balls. And now what is happening is that you are drawing a red ball from here. So now when you're drawing a red ball, the probability of drawing a red ball is actually 4/7 here. While you're trying to draw a red ball from here, there's a probability of drawing a red ball is 5/7 here, right? Now the red ball drawn from the bag one is known, a red ball drawn from the bag two is known, right? What they're interested in to know is that what is the total probability of drawing a red ball? So we are wanting to know the total probability of drawing a red ball. So what we are saying that, okay, so this is what we are saying that if you read this now closely, we are saying that probability of drawing a red ball given that it is from the bag one, and then probability of picking the first bag. Then plus probability of drawing a red ball given that it is from the bag 2 and into probability of drawing a bag 2 itself. Because I can choose this bag or this bag, right? So there are multiple branches which are being created, and then it's more like the sample space. It's this is sample space is actually partitioned. So it's not that everything is put together. That 4 plus 5 are basically 9 red balls, and then five white balls are put together. So then I know that what is my total probability of drawing a red ball because this will be dependent on 9/14, right? But here the problem is that the sample space is actually split in two sort of events. One is that there is a bag one which is containing some sort of red and white. There's a bag two which is containing some sort of red and white. And in such a case, if you want to find out the probability of certain thing, then it will be dependent on various different paths you will be taking, and that is when we actually make use of this.